Let me zoom in just a little bit. So last time we were at the section 5.3, right, or 5.4. Talk about the eigenvalue method for the homogeneous system. We first of all introduced what is eigenvalue. Eigenvalue is the solution to the equation of determinant of A minus lambda I of n equals 0. Okay, it is the solution to this equation. With the solution of eigenvalues, you can get eigenvector by solving this vector equation. A minus lambda I times vector v equals 0. Therefore, the vector v are called the eigenvectors. If you have taken linear algebra, you know eigenvectors are, a lot of times it's more than one. So you have eigenspace, and the one we can solve is the basis for eigenspace. We did example 1 of looking for eigenvalues and eigenvectors. And then we went ahead and introduced the eigenvalue method for homogeneous system. I want to emphasize this is only for homogeneous system, okay, when there is no other f of t in this equation. So it's only first order x prime equals a times x. Here a is the coefficient matrix. So we said if you have such a homogeneous linear system, we can get a solution x vector, which will be v any eigenvector times e raised to the eigenvalue lambda times t. The case 1 is when we focused on last time. Case 1 is when a matrix has distinct real eigenvalues, right? So we said if eigenvalues are different, then the eigenvectors would be linearly independent, which later on guarantees these x1, x2, x of n, these n solutions would be linearly independent solutions. Therefore, we can get a linear combination of these solutions to for us to get the general solution to the homogeneous system. That's the method we introduced last time. So basically the example 2, example 3 that we did last time is all from that method. Okay. But that's only in the case when the matrix A has distinct real eigenvalues. So in class today, we're going to continue to talk about a second case, which is when matrix has conjugate complex eigenvalues. Okay. So here, let's introduce the idea. All right, I have to read my pen. So suppose we have matrix A, and you can get the eigenvalues as the lambda. Okay. Let's assume that the lambda comes up as a complex number, A plus BI. And we know that lambda bar, which is its conjugate pair, A minus BI, would also be a solution to the characteristic equation. Because a lot of times it comes from lambda squared equals to some negative number, right? So it's going to be a lambda bar would also be a solution to the characteristic equation, which means this is also, these are both eigenvalues. Okay. So let's suppose the V, okay, so vector V is related to the first eigenvalue. This is the eigenvector associated with lambda. It's easy to show that the vector V will also be an eigenvector associated with lambda bar. Okay, lambda bar. So that means basically for the eigenvalue lambda and a lambda bar being two complex numbers, they would share the same eigenvector. Okay, share the same eigenvector. So then we can have xt, okay, vector x, which will be a solution, okay, as a general solution here. This is a general solution. General solution will just be C1 V e raised to lambda t plus C2 V, because it's the same eigenvector, right? C2 V e raised to lambda bar t, which is its conjugate. When it comes to complex numbers, we do recall this Euler's formula. Okay, e raised to I times theta would be cosine theta plus I sine theta. Then we can apply it to here and to there, okay, for this lambda t and lambda bar t. Eventually, the conclusion would be some coefficient C3 times the real part of x of t plus C4 imaginary part of x of t. Does this sound abstract, guys?
Yes.
Yeah.
All right, currently it's pretty abstract. Well, I'm going to demonstrate what we have just talked about here by using actual specific example. That might be helpful, right? Let's see how we get this imaginary part and how do we get this the real part, imaginary part, and how do we use this this Euler formula to get this conclusion in general. So we're going to take it slow and look at example 4. Example 4, solve the system by eigenvalue method. This is a system of only 2 unknowns, okay, and matrix A shouldn't be too difficult, right? So let's go ahead and follow what we did last time. So solution. First of all, we have the unknown vector x bar. X vector would be containing unknown x1 and x2. Good?
Yeah.
And what about matrix A?
1, -5, 1,
1, -5,
1, -1.
1, -1. Okay. Therefore, this system of differential equations basically could be written as a matrix equation, which is vector x its derivative equals matrix A times vector x, right? Again, this is homogeneous and it's first order. Everything good so far?
Yep.
All right, so if it's homogeneous and it's first order, we know we can use eigenvalue method, right? So use eigenvalue method. Okay. Okay, so first of all, let's go ahead and find eigenvalues. Which is the determinant of A minus lambda times I equals 0. This time, identity matrix will be of size 2, right? So I2. You guys all right?
Yep.
Yeah.
Okay, let's keep going. Therefore, we should have 1, -1, -5, 1, and we've said you can just subtract the lambda from the main diagonal entry. So we have 1 minus lambda, -5, 1, -1 minus lambda. Okay. All right, this is only a 2 by 2 determinant, so it's pretty easy, right? Just to cross multiply, so you have 1 minus lambda times -1 minus lambda, subtract -5 should equal to 0. All right, and then you do FOIL. So -1 plus lambda minus lambda plus lambda squared plus 5 equals 0. Good?
Yep.
Yep, so what do we have? We have lambda squared equals 2. These 2 cancels out. So lambda squared plus 4, right? Is that plus 4 equals 0. So lambda squared equals to
-4.
correct. -4, which means lambda 1 and 2 would be plus minus 2i. This is a pair of conjugate complex eigenvalues, right? Plus minus 2i. All right, so let's see how do we deal with these complex eigenvalues. Even though it's complex, we can just kind of like mimic what we did last time. Okay, so next, find eigenvectors associated with lambda equals to 2i. Okay, and we'll see the similar pattern for lambda equals to negative 2i. Kind of lambda 1 equals 2i, right? So basically, we're going to solve the equation, which is a minus lambda times I2, a minus lambda times I2, and then vector v equals 0 vector, right? For 8. Is that all right?
Yes.
So far, it's pretty much the same as what we did last time, right?
Yep.
Okay, so let's go ahead and just plug 2i in for the equation. So we have, okay, so we have, okay, a, so 1 minus 2i. So we have 1 minus 2i. And then this is a negative 5 here.
Yes.
And then 1. Okay, and then negative 1 minus 2i. Negative 1 minus 2i times v. Okay, let's assume we have two components, so the a and b. So a, b equals 0, 0. Is that good?
Yes.
All right, so we're going to continue from that system. All right, so we're going to just multiply this out, right? Let's see. So we're going to multiply this out. Multiply this piece with this vector. So we have 1 minus 2i times a. And then minus 5b. Okay. Minus 5b equals 0. That's the first equation. Second equation is 1 times a, and then plus minus 1 minus 2ib. A plus negative 1 minus 2ib equals 0. Okay, let's call this equation 1. Let's call this equation 2. How do we solve for a and b, folks?
We can multiply by the one, whichever one we decide to take out. I think we should take out a first.
Okay. So if we eliminate a, eliminate a, so we can do equation 2 multiply with 1 minus 2i, right? Okay, let's see what do we get. Equation 2 multiply 1 minus 2i. So we have 1 minus 2i, a, and plus negative 1 minus 2i times 1 minus 2i, b equals 0. This is equation 3. Okay, so that is equation 3. Let's simplify this. This is 1 minus 2ia. I'm going to ask you guys to calculate this negative 1 minus 2i times 1 minus 2i. What is that?
1 plus 4i squared.
Okay, 1 plus 0 is
Negative 1
1 plus 4.
minus 4.
Okay, so I'm going to do negative 1 minus 2i, right? And then plus 2i, and then plus 4i squared, which is negative 1 plus 4 times I squared. Is that just -1 minus 4? Yes, which is -5, right?
Yep.
Okay, so if you expand that, you could just get -5. Okay, let me see, where's my 10? Oh, over here. So -5b equals 0. This is just equation 3. Do you see equation 1 and equation 3 are exactly the same?
Yeah.
Yeah.
Okay.
So it's
Yeah,
not-
3 and 1 the same, which means, well, 3 comes from equation 2, right? 2 gets to 3, and then 3 is the same as equation 1. So in general, it's just telling you equation 1 is similar to equation 2, right?
Uh-huh.
Because equation 2 just turns to equation 1 later on. All right, so that means for this system, right, for the system 1 and 2, only one equation would be helpful, because equation 2 just repeats what you get from equation 1. Okay, I'm just going to say equation 2 would be work. Okay, work. Because equation 2 is easier. Okay, so equation 2 works, so that tells you that A, can I express A in terms of B from equation 2?
Yeah, -b. Or no.
A would be this whole thing, right? I can just move this whole thing to the right. So it isn't just 1 plus 2IB.
Yeah.
Mhm.
Right? And you just move this piece to the right. So are we almost there for the eigenvector? Okay, so the eigenvector V, which is AB, A is just 1 plus 2IB, and B would be B, right? So I can just take out the B and leaving 1 plus 2I1 here as kind of like the basis for the eigenspace. Okay. Make sense? So this will be just be
Yeah.
the representative eigenvector. Okay, right. Eigenvector, right? Good so far?
Yeah.
So the eigenvector associated with λ1 equals 2I, I just get it 1 plus 2I1. Okay. I'm going to let you guys try the eigenvectors associated with λ2, which is -2I. Okay. Okay, so next, find eigenvector associated with λ2 equals to -2I. You guys follow what we just did, and let's see what you can get for the eigenvector.
Quick question, Dr. Wu. Is there like a shortcut to this? Because it's like negative, so wouldn't you just flip it to 1 minus 2I?
1 minus 2I? Oh, you mean over here?
Yeah.
You'll see that in just a minute. Yes, go ahead and work on it. Once we finish this question, you're probably going to see the shortcut.
Okay.
Mm-hmm.
Dr. Wu,
Yes.
does MATLAB work with imaginary numbers to give eigenvector?
It should work for I. You can just enter I. That's for complex numbers.
For complex numbers, yeah, correct.
Mm-hmm.
I get eigenvalues, but I'm struggling with eigenvector.
Eigenvalues are easy to obtain this question anyway, right?
Yeah.
Mm-hmm. Okay, do you guys get this matrix set up as 1 plus 2i, negative 5, 1, negative 1 plus 2i, cd equals 0, 0?
Yes.
You may have used AB, that's fine. Okay, I'm just going to try it to be CD. Okay. Then you're going to have 1 plus 2i c minus 5d equals 0. And then c plus negative 1 plus 2i d equals 0, right? We call this equation 1, call this equation 2. And do we have the similar pattern coming up?
Yeah.
If you do equation 2 multiplied by 1 plus 2i, basically it's just 1 plus 2i times c, and then you get the same, right? Is it minus, you get negative 1 plus 2i times 1 plus 2i,
Yes.
which is the same as this, right? Okay. Which is minus 5d. Okay, so minus 5d equals 0. So equation 3, that matches your equation 1. So again, that just tells you equation 1, equation 2, they are redundant. Okay, only one equation would be enough for this system of equations. Okay. So that tells us c plus negative 1 plus 2id equals 0. Okay, which means c would just be 1 minus 2id, right? Okay, so this vector v now would be c d, and that's going to be 1 minus 2id times d. So again, you can pull out the d, you get a 1 minus 2i, 1, right?
Mm-hmm.
Okay, Eric, this is kind of similar to what you just guessed 1 plus 2i, replace that by 1 minus 2i. Okay. So I can say this will just be my representative eigenvector v2. I'm going to call the original one over here to be v1. Okay. Any questions so far, folks? Okay. Alrighty, now let's see. So then let's look at the solutions. Okay. Ooh, okay. Okay, so then I'm going to get x1, which is based on our method last time. It'll be v1 e lambda 1t, and x2 would be v2 e raised to the lambda 2t, right?
Yeah.
Okay. Let's do x1. Okay, so x1 would be v1. So v1 is what we just looked at here. It's 1 plus 2i1. So 1 plus 2i1, that's v1, e raised to lambda 1t. So e raised to the lambda. Lambda this time is 2i. So 2it. Good?
Yes.
Okay, now here you're going to use the Euler's formula. Euler's formula, e raised to the I theta. What's e raised to I theta?
Cosine theta. Plus I
Cosine
sine.
theta, so like x value plus I sine theta, right? So do we have e raised to 2it here? And if you just match this, so it's the e raised to 2it. So you see the theta would just be 2t, right? You guys following me?
Yes.
Yep.
Okay, so you just replace the theta by 2t. You have cosine 2t plus I sine 2t, right? Okay, so I'm going to write this e raised to 2it as, okay, so 1 plus 2i, 1, and times cosine 2t plus I sine 2t. Okay. All right, so let's see. What can we do? We can distribute, we can just multiply this cosine 2t plus I sine 2t to the two components, right? So the two components will be 1 plus 2i times cosine 2t plus I sine 2t. And the bottom will just be cosine 2t plus I sine 2t. Good so far?
Yeah.
Yeah.
Okay, now let's expand this 1 plus 2i cosine 2t plus I sine 2t. All right, so expand it, you're going to have cosine 2t. And then the imaginary part, cosine 2t plus 2i cosine 2t. And then plus I sine 2t. And here is minus 2. I'm running out of space. Minus 2 sine 2t. That's the first part. And then here's cosine 2t plus I sine 2t, right? Okay. And over here you can see that part of them is imaginary part, right? Which is along with the i's. Part of them is only just the real part, cosine 2t, negative 2 sine 2t, and then cosine 2t in the bottom. So that is x1. Similarly, can we get x2? let's see, where's my, okay. X2 vector would be V2, right? V2. So V2 would be 1 minus 2i, 1, e raised to the negative 2it. Is that good?
Yeah.
Okay. I'm going to do a little bit of side work here because eventually you're going to see what's e raised to the I times negative 2t, right? Negative 2it over here. That should be cosine negative 2t plus I sine negative 2t. All right, folks, I'm going to ask you, is cosine negative 2t the same as cosine 2t?
Yeah.
Yep, because cosine function is even. So cosine negative 2t is the same as cosine 2t. What about sine negative 2t compared to sine 2t?
Negative I sine 2t.
Yep, because sine is odd function. So minus I sine 2t, right? You see the sign over here just changes in front of the I. So I can write this as 1 minus 2i, 1, and then cosine 2t minus I sine 2t, right? If you simplify it. All right, so eventually we're going to mimic what we just did there. We're going to distribute this cosine 2t minus I sine 2t to both of that. You have 1 minus 2i times cosine 2t minus I sine 2t. And the bottom will just be cosine 2t minus I sine 2t. Okay, so then we're going to distribute the cosine 2t. FOIL, you have cosine 2t minus 2i cosine 2t minus I sine 2t. And here you have plus 2i squared, which is minus 2 sine 2t. The bottom, you get a cosine 2t minus I sine 2t. Folks, if we observe what we see here, x1 and x2, what do you see here?
Only i's change the sign.
Only i's got changed, right? Because let me see here. Only i's has got the sign interchanged. Otherwise, the rest of them are all the same, right? The real parts are the same. Real parts, real. All the real parts are the same. All the imaginary parts are the same except for the conjugate, being conjugated, right? And here you sort of had x2 vector is x1 vector is conjugate. See that? Right, the conjugate of x1 vector. Folks, you see that?
Yep.
Okay, so let's see. All right, so therefore, let's see. Here's our tangent. Oh, here. Therefore, the general solution will be x bar. Okay, let's use whatever we learned last time. So C1 times x1 plus C2 times x2. Okay, I'm gonna do a little bit kind of like symbolic thing here. Okay. I'm gonna say x1 would be, let's see, because we've used A, B, C, D, all right? So let's say x1 is E plus IF, and here is G, E, F, G, H, I. Over here, E and the E, F, G, H is just representing these cosine and sine. You guys see what I'm saying?
Yes.
Mhm.
Okay, I'm gonna say these are the E, or these two are the E, because the E plus I, G, and then here will be EF, and here will be G plus IH. We will just explain that just in a minute. And the C2, because X2 is X1, it's conjugate, it was just going to be E minus IF, right? IF, not if, and then G minus IH. Right, C1 plus C2. Okay, eventually what do we have? Can we sort of combine those two?
Yeah.
So you can get sort of, let's see, what do we have? We can combine EG, this vector, right? So the EG, okay, with constant C1 plus C2. And then for the FH, part,
They cancel out.
they don't really cancel out. Okay, they have eyes, right? Okay,
Yeah, I
so
was
eyes
wondering.
in front. But then the coefficient turns out to be C1 minus C2. You guys see that?
Yeah.
Right. Okay. All right. So here, let me again just kind of like rephrase with my E, F, G, H. Okay, in case you are confused here. Let me use another color here. So I'm going to say here. Okay. So this will be my E. Okay, E would be cosine 2t minus 2 sine 2t, which is the real part of the first component. And F would be the imaginary part of the first component. So that'd be 2 cosine 2t, 2 cosine 2t plus sine 2t. Okay, G would be the real part of the second component, cosine 2t, and H would be the imaginary part of the second component. So that's the EFGH I'm referring to over here, EFGH. Is everything good so far, folks?
Yes.
Yeah, I have one question.
Sure.
Whenever we have imaginary eigenvalues, we are gonna have cosine and sine because of Euler's formula. Correct?
Because always, yeah, you're gonna have cosine and sine.
Okay.
Remember in chapter 2, if you guys recall in chapter 2, if you have complex roots to Kepler's equations, don't we have cosine and sine coming up again?
Yeah.
Right? And so cosine and sine is the one that you see all the time for complex roots. All right, so we are over here. So I'm going to say in the end, okay, the C1 plus C2, can this be considered as a constant?
Yeah.
Yes, I'm just going to say this is just a C3. Okay. And C3, and I'm just going to write E and G. So E is cosine 2t minus 2 sine 2t. Cosine 2t minus 2 sine 2t. I'm running out of space here. Minus 2 sine 2t. Okay, so that's E. And my G would be cosine 2t. Okay. Similarly, for the C1 minus C2 times I, can I say this is another constant?
Yeah.
Right? Let me call this to be constant C4. And FH will just be FH. So 2 cosine 2t plus sine 2t. And then H will just be sine 2t. Okay, and let's see, what are these two items actually, if you look at it? The part that we have pulled out, right, this vector and this vector. Cosine 2t and a minus 2 sine 2t comes completely from the from the real part of the e raised to lambda t, right?
Mm-hmm.
So this part is actually just c3 times real part of vector v e raised to lambda t. And the second part over here, 2 cosine 2t plus sine 2t, sine 2t. Let's go back to the original vector. So 2 cosine 2t plus sine 2t, in the bottom sine 2t. They come from the imaginary part of this v e raised to lambda t. Imaginary part of v e raised to lambda t. And you may ask, well, there are two lambdas, lambda 1 and lambda 2. But based on what we did over here, the lambda 2 is just a conjugate of lambda 1. So even if we follow our old procedure, right, we come up, see the same amount would appear in your v2 e raised to lambda 2t, which is in your x2. And these part are just, these functions we extracted would all be the same from x1. So actually the shortcut here will just be, if we just do v1 e lambda 1 and v1 e lambda 1, it will be sufficient to cover this general solution. Guys, let me just rephrase what I just did, okay? Even though we find x1, x2 by using v1 e raised to lambda 1t, v2 e raised to lambda 2t, but we see that the x1, x2, they are related in the sense x2 will just be the conjugate of x1, right? So in fact, you can save your time. You don't have to do all of these. Okay? Let me just box out the part. So in fact, all these parts could be saved. Okay, you don't have to do this. Not necessary later on. Okay. You don't have to calculate these by hand because we know x2 will just be the conjugate of x1. Okay. So eventually, all the general solution will just be based on this x1. Make sense, folks?
Mm-hmm.
And this is what I'm going to say as the shortcut. Okay, so this will be the shortcut. Shortcut will just be focus on lambda 1 and v1. Okay. You only need to focus on one part of the conjugate, one part of the eigenvalue and its eigenvector. That should be enough for writing out the general solution. Does this sound too abstract still?
It makes more sense now.
Yeah. It's gonna save time.
Okay.
On the second part.
How about we just use the shortcut method and do this example 5, and then we're done today.
Okay.
Okay, so example 5, we're just going to do this in the shortcut method if it applies. Okay. So this system, you have x1 prime equals x1 minus 2x2, x2 prime equals 2x1 plus x2. All right, so here we're going to have unknown vector x would be x1, x2, and matrix A will just be 1, -2, 2, 1, right? And again, we have the equation, the x prime equals ax, which is homogeneous in the first order. So let's go ahead and find eigenvalue of matrix A first, right? So we said we're going to do lambda A minus lambda I2 equals 0. Folks, you guys are there?
Here.
Okay, let's go ahead and get this 2 to determine again. So 1, 1, -2, 2, and I'm going to subtract lambda here equals 0. I'm going to ask you guys to find the lambda. Okay, do you have this quadratic equation of lambda squared minus 2 lambda plus 5 equals 0?
Mm-hmm.
Yeah.
Okay. Yep, so you can use quadratic formula. So you can say lambda will be 2a negative b plus minus b squared minus 4ac if you don't recall that quadratic formula. Okay. 2a, a will be coefficient of lambda squared, which is 2. Negative b will be 2 plus minus b squared, which is going to be 4, minus 4ac. So 4 times 1 times 5, right?
Yep.
Which is 20. Okay, so you come down to 2 plus minus square root of negative 16, which implies a complex number coming up. So that's 2 plus minus, what is the root of negative 16, folks?
Right.
Y. Okay, therefore we just have 1 plus minus 2i, right? Which is a pair of conjugate roots. Okay, conjugate roots. So we have 2 conjugate pairs of eigenvalues. So I can say lambda 1 equals to 1 plus 2i. Lambda 2 is 1 minus 2i. However, since we have got this conclusion from example 1, you can just take the shortcut. The lambda 2, you don't have to pay too much attention to lambda 2 because we can save work for lambda 2. Just focus on the lambda 1. Okay. So once we get the lambda 1, we're going to go ahead and find eigenvector for lambda 1 equals 1 plus 2i. You still need to do this work, okay? Eigenvalue and eigenvector still needs to be found. Okay, so we're going to do a minus, we're going to do a minus lambda 1 I2 times vector v equals to 0 vector, right? Which would give me this equation. Here, vector v, again, still have 2 components, A and B. So A, B. And I'm going to have the lambda plug-in, which is 1 plus 2i. So 1 minus 1 plus 2i, negative 2, and here is positive 2. 1 minus 1 plus 2i equals to 0, 0. You guys have this?
Yes.
Okay. Actually, this question is easier than the previous one because the coefficients are better. So we have 1 minus 1 minus 2i. This turns out to be negative 2i, negative 2, and 2, negative 2i times AB equals 0, 0. All right, let's go ahead and do matrix multiplication. Okay, so this row times this column. Negative 2ia minus 2b equals 0. And second, we have 2a minus 2i times b equals to 0. Equation 1 and equation 2. What do we do next, folks?
We can get the substitution pretty easily.
Okay, you can do a substitution. Or, yeah.
We can just subtract or add 1 to the other side and get it that way, just using the normal first equations.
By the way, there's a bunch of 2's over here. I'm going to reduce all the 2's. Okay, 2, 2, 2, 2. So I'm going to reduce all the 2. Right?
Yeah.
Okay, and suppose from equation 1, I can say b equals equation 1. B would be negative ai, right? Can I put this into equation 2?
Yes.
And then I would have a minus I times b equals 0. What do we have here? A plus a I squared equals 0, right?
Mm-hmm. So it cancels out.
Yeah, it's just a minus a, which is 0 equals 0. What does it tell you? 0 equals 0.
There's infinitely many solutions.
Yeah, it
No
means
solutions.
always this is always true, right? This is always true. Basically, what it tells you is once I change the lux b equals negative ai, this equation 2 always works. Right, this equation 2 always works. What it further tells you is basically b is going to be negative ai. As long as b equals negative ai, the equation 2 always works. Okay. If you check equation 1 and equation 2 one more time, you can tell that equation 2 is redundant. Okay, equation 2 just repeats the information from equation 1. So these two equations, actually equation 1 is kind of the same as equation 2, okay, by nature. Okay. So the vector z, which is the eigenvector, can be written as having components a, b, right? And this time I can just replace the b by negative ai. Good?
Mm-hmm.
Yes.
Let's pull out the a. So I'm going to have 1 negative I. All right, so I'm going to just call one more time this 1 negative I, this vector to be my v1, okay, v1 vector. which is the eigenvector, the representative eigenvector related to lambda 1 equals to 1 plus 2i. So quick question. Okay, let me see what so note for lambda 2, which is 1 minus 2i, what's going to be its v2?
1i.
Yeah, so you just do 1i. So we don't really need this information for writing out our general solution. Okay. So that's something easy to obtain, right? Okay. All right, so next we're just going to go ahead and write down the general solution based on what we did last time. So next, we're going to try to find general solution by the shortcut way. Okay. This shortcut method is based on the experience we obtained from example 1. Okay, example 1. We figured out eventually what's useful will just be v1 e raised to lambda 1t. Okay. Right, v1 e raised to lambda 1t, which is just your x1. x1 is useful. Okay. So let's go ahead and still do this x1. Okay, so let's figure out x1. x1 is v1 e raised to lambda 1t, right? You guys all right?
Yes.
Let's copy my v1. v1 is 1 negative I. E raised to the lambda 1t. So what's lambda 1?
1 plus 2i.
1 plus I. Good. So we're going to say 1 plus 2i t, right? Okay. Now remember, e raised to 1 plus, okay, e raised to 1 plus 2it. Can I separate this into two parts?
Yeah.
E to the t.
Times
The e raised to the 1, right, times e raised to 2it, correct?
So wouldn't be 1 plus 2i be in the parentheses?
Yeah, wouldn't it be e to the t times 2it?
Oh, yeah, my bad. You guys are right. No, yes, it'll be in the parentheses. So we should have a t, right?
Yeah.
The e raised to t plus 2it, my bad. So the e to the t times e raised to 2it. Good so far? And for this e raised to 2it, can I use the Euler's method again? Euler's formula?
Yeah, cosine 2t.
Cosine 2t plus I sine 2t, right? Okay, so let's go ahead and replace this exponential function by this. Okay. So I'm going to say 1 negative I, and there's an e to the t. I'm going to write e to the t to the front, and times cosine 2t plus I sine 2t. Questions? So far, so good, folks?
Yeah.
Okay, we're close to the end. Okay, so we're going to keep the e to the t as it is because it doesn't have anything to do with the cosine and I. I'm going to put e to the t to the front. And then I'm going to distribute this cosine 2t plus I sine 2t to both of these two components. So I'll have cosine 2t plus I sine 2t. To the bottom, I'm having negative cosine 2t times I, so that's negative I cosine 2t. I'm also going to multiply negative I with I sine 2t. What should I have?
Plus sine 2t.
Correct. So this is sine 2t minus I cosine 2t, right?
Yeah.
All right, so let's split. You see the imaginary part, which after I. This will be the imaginary part. This will be the real part. Let's split that into two. So e to the t times cosine 2t sine 2t. This is the real part, right? The imaginary part will be I, okay, pulled out. And you still have e to the t. What's left would be sine 2t and negative cosine 2t. Here would be the imaginary part. Is everything good?
Mm-hmm.
So this is the real part of x1. Here is the imaginary part of x1, right? Now we can just write down our general solution based on our experience from the previous example. So the general solution x bar. Okay. Let's see. Therefore, the general solution x bar would be some constant. Since we haven't used the C1, C2, I'm just going to say C1 times imaginary part of x1, a real part, and plus C2, imaginary part of x1. Okay, so just use this conclusion that we did previously. Let me box this part out. So here, okay. Okay. So we're just going to apply over here. We have C1 times real part, which is just going to be e to the t cosine 2t. Sine 2t. And plus another constant C2 times the imaginary part of x1, which would be e to the t sine 2t, e to the t sine 2t, and negative cosine 2t. Is this quicker than what we did previously?
Yeah.
Right? Because you don't have to work on the x2 part, right? X2 part, this part could all be saved. You don't have to do this part at all. You can just go straight to the conclusion based on what you get from x1. All right, hold on. Let me kind of finish up here. Just want to explain in case you're still confused here. This is my solution x, which contains two unknowns, x1 and x2, right? So the solution, you can just say x1, x2. So solution x1 and solution x2. x1 will just be c1 e to the t cosine 2t plus c2 e to the t sine 2t. And the second unknown x2 will just be c1 e to the t sine 2t minus c2 e to the t cosine 2t.
I just have one quick question.
Sure, Philip.
When you wrote the C2 e to the t, why did you not write down the I e to the t?
Yeah, good question. The reason I'm not writing I is you can write I here. But remember, if it's a constant times I, is that still a constant?
Oh, okay, yeah.
That could be absorbed, right? That
I
could be
get it.
absorbed into the C2. So you see that when I'm looking at an X1, I specifically said this part is its real part, and this part, which is the e to the t, sine to t, negative cosine to t, this part is its imaginary part. But only take out the imaginary part.
Okay, I get it.
Make sense? Mm-hmm.
Yep, thank you.
All right. Is everything okay?
Yes.
Okay. How do we get C1 and C2? Let's see. Assume we have initial condition. Initial condition that's given. X1, 0 is 0, and X2, 0 is 4. What can this initial condition help us to do?
We can.
What can you,
C1, C2.
yeah, so we can use this to determine C1 and C2, right? Okay, remember T is the variable. So X1 is a function of T, X2 is a function of T. If I just do that real quick, I'm going to plug 0 in for T. So T equals 0. X1 of 0 would be 0 equals 2. C1 e to the 0, which is 1, cosine 0, which is 1, plus C2 e to the 0, which is 1, sine 0, which is 0. Is that correct, guys?
Yep.
Yeah.
So C2 here, this part doesn't really matter, right? It just tells you C1 would be 0. Okay. For the second initial condition, and we can get an equation, X2 at 0 would be 4. And this part vanishes because sine 0 is 0 minus C2. So negative C2 e to the 0, which is 1, cosine 0, which is 1. So I get C2 is negative 4. So you can get a particular solution, right? Particular solution will just be, particular solution will just be X1 of T, X2 of T. Substitute C1 and C2. So C1 part is all zeros. So this part all is gone. And in the second part, we have negative 4 e to the t sine 2t. Also, we have positive 4 e to the t cosine 2t. And now we got to this particular solution to the initial value problem. Suppose you are given with this initial condition, right?
Yeah, that's fine.
Okay, any questions for example 2? We'll try to use the shortcut method. Okay. It does save a little bit of time, right?
Yeah.
Let me quickly go over what we did, okay, real quick. So starting from today, you can just use this shortcut method for the complex eigenvalue, those cases. So basically, you first of all find some lambda 1, lambda 2, assume they're conjugate pairs. Then we just do lambda 1, find its eigenvector, which would be V1, and use this V1 and lambda 1 to get X1. Over here, you have to use the Euler's formula. Okay. Once you get X1 at X1, you recognize its real part and you recognize its imaginary part. Use these two to write down the general solution. The general solution, which would be C1 times its real part plus C2 times its imaginary part. If there is C1, C2, we can use initial conditions to determine C1 and C2 for particular solution. All right, that's it that we have left for this section. Any questions, folks?
I have one question.
Yes, Noam.
If we have lambdas where one lambda is real and the other two are imaginary, like in our homework, then we solve imaginary part like we did today and real part like we did on Friday, and then merge the two solutions.
Yeah, you
Or-
just do the linear combination, right? For the pair of complex eigenvalues, you just follow our method today. You'll get a part of that. I mean, you'll get a C1, C2, blah, blah, blah. And for the real solution, you probably just want to add a C3.
Okay, C3. Yeah,
Right.
that's fine. Yeah,
Yeah, linear
makes sense.
combination.
Yeah.
Make sense?
Yeah.
Any other questions? No problem.
Dr. Wu,
Yes, Eric.
so the schedule, like moving forward, would be just prepping for the final.
Final will be take home. Yeah. What's the question you have?
I think this Friday is holidays, right?
Yeah, correct. Well, is that Agan?
Agustin, you always want to skip class.
Yes, yes.
Crazy.